Growth and decay. Growth and decay is just a normal equation, a normal exponential equation, just you might have to consider in a certain situation. Growth is something keep going more and more, and decay is getting less and less. In the cases that we usually have population with the growth, or cell or chemical reaction, so in some case we might have something like this. So the population of bear, seriously, I just make up some numbers. So population of the bear T, originally in a certain farmyard or something. So there's not in a certain area. There's 25 bears, and it is growing in the exponential growth of 0.8 T per year. So that's not initial, but then this is growing in exponential per year. So number one, what is the initial population? How to spell initial? INITIAL. Sorry. Does it look right? Anyway, the initial population dead. Initial population is that when T equals to 0, initial T equals to 0. So you just find that 25 times 2 to the power 0.18 times 0, which is 0, which is 25 times 1, usually is 25. The question will ask you to just write down the information, because by common sense, you know anything multiplied by 0 is 0, and anything to the power 0 will be 1. So they will usually no step at all, you just write it down will be fine. So now, how about we have when after 3 years later? So we have B3 equals to 25 times 2 to the power 0.18 times 3. Alright, that is time when you use your calculator. Alright, back to normal calculation. So I have 25 times 2 to the power 0.8 times 3. No brainer, you just calculate it. And that is the trick of it. Remember, no matter you round up or round down, the population have to be a whole number. So usually people will accept 26, 36 or 37, but not 36.3, because we will not have like half of a bear. Like you cannot have just the limbs coming up or whatever. And that morally it depends on how things get, how people think that, oh, it started, it have a life, so it is a bear. So you can count that. Or vice versa, you can say that, oh, it's not fully produced out of the mother's body, so it's not. Whatever you argue it, definitely have to be a whole numbers. Alright? And another thing, like you might need to think about, there's money and compound. I'll talk about that when we go to log as well. Alright, so this is one thing. Another exponential growth, the compound interest. The interest bit will be another exponential growth. So we have amount equals to principal times 1 plus our percent to the power t. Alright, this is the time when you have the complete years. So we have P, say for example, for $1,000, and the interest rate is 2%. So in 3 years, so that should be a no-brainer for, like, you should learn it in year 9. So 2% to the power 3. Nice and easy. That's 1,000. That's another exponential growth, supposed to be. But you may say that in the real life, there's not getting any money from the bank. No, the interest is there, just the charges is more. So we have 1,000 times 0.02 to the power 3. Yep. And then for money, you can have 2 decimal places or 3 significant figures. It really depends on the question it says. Alright, so we can go to the decay. Decay is sometimes, usually is radioactivity. Physics people might need that a bit more. So, and they usually call it half-life, but it decays on a substance or something. So we have, say for example, a decay of a substance, whatever it is, I'm bad in chemistry. So we have the weight of it is, the model is something like this. All right. So initially, oh, that's very right. Initial weight should be 250 because t equals to 0. Initial, again, initial means t equals to 0. So t to the power 0, something to the power 0 is 1, so it's 250. So in 40 years, so we have W40, just like function, equals to 250 times 0.97987 to the power 400. And let's see. Okay, 400 years later, it will be dropped down to 1.33, to 3 significant figure. Some markers tends to make sure you write that down. For me, it's fine, just in case you need to be aware of it. And that is the basic decay and growth.